Okay, so find your sheet that's got the buffer solutions stuff on it here. And let's go forward with looking at how these buffers work. So we decided that a buffer solution is a combination of a weak acid with an ionic compound that has the same negative ion. So we did acetic acid and sodium acetate. So that was the acetic part of acetic acid is the acetate ion. And so we combined it with some sodium acetate because it had the matching negative ion. And the entire purpose is to create something that protects against change in pH. So we can add a little bit of acid and a little bit of base, and the pH doesn't change significantly. It fluctuated a little bit, but not a whole bunch. The way a buffer solution works is because a weak acid is in equilibrium. So when you had just the acetic acid, you had an equilibrium that had lots of acetic acid and a little bit of hydrogen ion and a little bit of acetate ion. When you added the sodium acid, and I guess so originally we're going to label it, we had lots of this and just a little bit of these. When you added the sodium acetate, you then also got some extra acetate ion. And now you have a situation where you have a lot of the anion with the hydrogen attached and a lot of the anion with the hydrogen not attached. So this piece right here would only have a little bit until you added the sodium acetate, and these acetate ions added to the collection of those over there. So now we have a system that has lots of this, and a little bit of hydrogen. When you added an acid to this, that's the equivalent to adding hydrogen ions. If we think back to what we learned about Le Chatelier's principle and the shifting of equilibrium, if you add more hydrogen, the equilibrium, because the hydrogen's being added, shifts back that way, and the hydrogen ions don't build up. The job of this stuff is essentially to gather extra hydrogen ion. So if you add extra hydrogen ion, because you have so much acetate, the acetate ions can grab the extra hydrogen ions, package them up, and bring them over here where they don't have any impact on the pH because they're packaged up with an acetate ion. So this is kind of like a hydrogen ion scavenger. Oh gee, there's too many hydrogen ions, let's grab some of them and pack them up and pull them over here where they don't impact the pH anymore. If you add a base, like sodium hydroxide, the situation is slightly more complicated. But we're adding hydroxide ions. Those hydroxide ions react with the hydrogen ions to produce water. So the net effect is that of removing the hydrogen. That should cause the pH to drop, except that we have a way to replace those. If these start to disappear, the equilibrium shifts to the right. These guys start falling apart and replacing the hydrogens. So the function of the weak acid portion of the buffer is to fall apart to replace missing hydrogen ion. So the overall result of this kind of fancy system here is that the concentration of the hydrogen ion remains relatively constant. And because of that, pH doesn't change much. And we're able to achieve this because the C2H3O2 minus binds up any extra hydrogen, and the HC2H3O2, the acid part, replaces any missing hydrogen. And so you have something to fix each situation. Because remember, in the beginning, we set ourselves up to have lots of this. So we had plenty of that if we needed to replace any missing hydrogen. So as you added the base started to eat up the hydrogen. These just started to fall apart to replace the hydrogen as it disappeared. Or if you add acid, there's too many H positives. Because you have an excess of these acetate ions, the acetate ions snag the hydrogen, tie it up so it can't contribute to the pH. And so you essentially have something that protects from each of the possible situations here in terms of, do I have too much hydrogen ion? Do I have not enough hydrogen ion? We have something to protect from each of those. Without adding this piece, we don't have that protection. That's why it had to be a two-part system. You had to have the acetic acid, but you also had to add lots of the acetate ion. Otherwise, you don't have a buffer situation. A weak acid alone can protect against the arrival of a little bit of base, but to get the full buffering effect, you have to have both of them. There is a formula that you can use to calculate the pH of a buffer system. And this is often important if you're going to be taking a college biology lab, because a lot of times in biology lab, you're trying to recreate the conditions inside a living organism. And so you need to start by making some kind of a buffer solution to hold the pH constant while you study the bacteria cells or whatever it is that the plant cells, whatever it is you might need to be studying. So you need to know how to get the proper pH of your buffer system. You might create a buffer that buffers the pH at 5.2 when you wanted to study cells that only live when the pH is above 8. Well, that's not going to do you any good. You have to get the buffer solution to be at the proper pH for whatever you want to do. This is the formula for calculating the pH of a buffer solution. The pH of a buffer solution will be the pKa plus the logarithm of taking the anion and dividing by the acid. pKa is a lot like pH. pKa is the opposite of the logarithm of the acid dissociation constant. Just like pH is the opposite of the logarithm of the hydrogen ion concentration. The anion is the concentration. We're just going to give it a generic name, A minus. For anion, it could be any anion. And the acid is that anion with some hydrogen attached. Remember, the Ka is the acid dissociation constant. That comes from a table. It's just a number that we would look up. And you have this table on the previous page that has a list of weak acids and their Ka values. So here's our acetic acid we used. We'll label it. And it has a Ka value of 1.8 times 10 to the negative fifth. So these are just numbers that you look up. This table is going to be provided for you on your test so that you can look up the Ka that you need. I think your textbook actually has an even bigger version of this table. Okay, so let's try a couple of examples. I moved the equation to the top of the next page just so you wouldn't have to keep going flip-flop, back and forth here. So our buffer solution had 0.83 molar of acetic acid and 0.60 grams of sodium acetate. Calculate the expected pH. So we got to go kind of looking for all of the pieces and what they are. So this piece right here, this 0.83 molar HC2H3O2, that is the concentration of the acid. It's the piece we're going to have to put in right there. This stuff is acetic acid. So we need to go back to that table and look up the Ka for acetic acid. So go back to our table. It's written a little bit differently, but this is acetic acid, 1.8 times 10 to the negative fifth. We've got it written as HC2 We've got ours written as C2H3O2, which is the two C's, the H3, the O2, and the H. So we've got ours written a little bit differently. So 1.8 times 10 to the negative fifth. So that number we looked up in a table. Look this up. So that's how we're going to get that number. We need to calculate the pKa, which is the negative log. So we need the pKa, which is the negative logarithm of the Ka, which is 1.8 times 10 to the negative fifth. That's going to take a calculator. Okay, let's take the logarithm 1.8 e change the sign. So the pKa here, following the rule we did with pH, that if this number has two significant figures, I'm going to keep 2 decimal points when I take the logarithm. 4.74. So I keep 2 decimal places here. Okay, so I've got that piece. So pKa, I've got that piece now. All I've got left to find is this anion piece. And that piece is going to come from this piece of information right here. I've got 0.60 grams of sodium acetate. I need to find the concentration of the acetate ion. Okay, so first I need to find out how many moles of sodium acetate. 0.60 grams, NaC2H3O2. So get your periodic table because we're going to need a molar mass on that stuff. Sodium plus C2. You guys get something in the ballpark of about 82-ish? Okay. Mole of NaC2H3O2 weighs 82.034 grams. Grams cancel. 0.6 divided by 82.034 means I have 0.0073 moles NaC2H3O2. And because every one of these has one acetate ion, I have 0.0073 moles of the anion, which is the C2H3O2 minus. Now, we unfortunately still aren't there. Because this doesn't say how many moles of anion, this says concentration of anion or molarity of anion. However, even though I took them away from you, we know if we look back in the little sheet that described the preparation of our buffer solution, making a buffer. Haha. We did this in 80 milliliters of solution. So if we take this, we can find the concentration of the anion by taking the moles of anion and dividing by 80 milliliters, but that's got to be in liters. So the concentration of my anion is 0.0073 divided by 0.08. .091. Okay, and that is that piece right there. And I've pretty much run out of space, so I guess I'll make my calculation up here. So if I want the pH of the buffer I made, I just have to grab all these pieces. I found the pKa, 4.74, plus the logarithm of the concentration of the anion, which I found right here, divided by the concentration of the acid, which was given to me in the problem. And then I should work this all out. pH is 4.74 plus the logarithm 0.091 divided by 0.83, the log of 0.11, log of 0.11 is a negative 0.96. So 4.74 minus 0.96 So the pH of the buffer solution we made was 3.78. And there we go. All right, work with your partners. Try this next one. I will work along kind of slowly up here, so if you get stuck, you can pop your head up and see how I'm doing. But try to do the same thing with this one right here. I'm going to start by identifying all the pieces that are going to help me. I got 9.5. Did I do good? Okay. So barring no atrocious math errors. And you'll notice how I did the work kind of in little chunks. Like I went looking at everything in the problem and decided what was it going to get me. That being told the Ka was for the purpose of getting the pKa. And so I did that little piece. Being told the mass of this ionic compound was for the purpose of getting the concentration of the cyanide ions. I was flat out told the concentration of the acid, and so that number I could just take with me. So I kind of thought about what was each piece of the information giving me and what could I do with it. I did those 3 pieces, and then I dropped them into the equation that goes with this. Now, at first this seems like, oh my gosh, I've got to be wrong, because they said that I started with this HCN, which is an acid, but now I have a concentration, which is actually, or a pH that says that my buffer solution is actually basic. And at first that seems a little bit weird, but it's an equilibrium situation. I started with the weak acid HCN, which if used by itself creates an equilibrium with H positive and Cn minus, and because it's got these hydrogen ions in it, it's an acid. However, if I come along and I add lots of cyanide ion, which I did, adding that lots of cyanide ion causes the equilibrium to shift back to the left again. And in shifting back to the left, I have apparently added enough cyanide ion to snag enough of these hydrogen ions from the acid, pushing them back over here to actually take the pH out of the acidic range and into the basic range. The cyanide ion grabbed so many of these that we got rid of them, and when we get rid of them, the pH is going to go up, could go up even to the point that it becomes basic, and in fact it does. If I had added less cyanide, I might not have had enough cyanide to pull all the hydrogen over here, but I pulled so much hydrogen over here that we actually fell into the basic range. And that will happen. You can create a buffer in the basic range using an acid as long as you use enough of the anion to pull enough of the hydrogen over to the other side. Now, there are limits. If you had taken this entire bottle of hydrochloric acid yesterday, or 2 days ago, and dumped it into your 80 milliliters of buffer solution, you could definitely overwhelm the system. Boom. Yeah, you could get the pH to change. That's something called buffering capacity. And you can add too much acid and too much base to overwhelm the buffering capacity. You're going to get the best buffering in both directions if you have an equal concentration of the acid and the salt. That protects you from adding both acids and bases. What this means is that you're going to get your best buffering system when the pH and the pKa of your solution are really, really close. So when you pick an acid to start with to build your buffer solution, pick one that's got a pKa really close to the pH that you desire. If you know that you need to specifically protect from one or the other, you can make the buffer solution with extra acid to buffer against the addition of base, or make it with extra anion to buffer against the addition of acid. Usually you know when you're preparing your buffer solution what you need the most protection from. Now, this next part looks complicated. We're not going to do much with it. I just want to kind of point some stuff out to you because you're going into the medical field. Especially if you end up in an emergency room or in a pulmonary environment where you're dealing with breath, pH buffering in your blood is going to be very, very critical. Your blood is naturally buffered between about 7.35 and 7.45. Remember that pH virtual lab we did where it lets you fill up the tank with blood? Blood is ever so slightly basic. The primary disruption to your blood pH is the buildup of carbon dioxide. Some of the CO2 produced by your cells has to be carried back to the lungs for elimination. but the rest of it dissolves in water and it produces this equilibrium. So this is carbon dioxide coming from your cells, reacts with the water in your bloodstream to make this carbonic acid. The carbonic acid, being a weak acid, creates this situation which acts as a buffer against changes in pH. So your blood has these two equilibrium going on. If you get too much carbon dioxide built up in the bloodstream, so let's say you have a patient who's having breathing difficulties. Obviously with COVID patients, this is one of the primary reasons that they're in the hospital. They're having breathing difficulties. If your lungs aren't functioning properly, you start to build up too much carbon dioxide in the bloodstream. I should have added and COVID here. This buildup takes the first equilibrium and shifts it this direction. With too much CO2, that starts to push this in that direction. So too much carbon dioxide in the bloodstream leads to having too much of this H2CO3, which is carbonic acid, in the bloodstream. So the net result of the lungs not getting rid of the carbon dioxide is that this builds up too much. And once you've got too much of this, this equilibrium shifts this way. The hydrogen ion concentration goes up. And as that hydrogen ion concentration goes up, the pH goes down because your blood becomes too acidic. They call it respiratory acidosis because too much acid has built up in the bloodstream, but that acid comes from your body's inability to expel the carbon dioxide. To fix this, they give the patient sodium hydrogen carbonate. Basically, an IV solution of baking soda fixes this problem because that increases the concentration of the hydrogen carbonate ion, which drives this equilibrium back that direction, leveling the pH in your bloodstream. So if you add extra of the hydrogen carbonate ion, which is what you get from the baking soda, you can undo the damage by pushing the equilibrium back the other way. So people with respiratory difficulties are often administered IV baking soda, I mean it's dissolved in water, in order to treat the pH problem in the blood. So that's one possible thing that can be going on with patients whose lungs aren't functioning properly. And that little equation was supposed to be on the previous page. So this was supposed to show if we have extra HCO3, we can shove this back the other direction, and pH rises back to normal. So I guess we should do it in 2 steps. If we drive this back, the hydrogen ion concentration goes down, pH rises back to normal. Okay. So respiratory distress causes the blood to become acidic. The blood that's acidic can be treated with intravenous sodium hydrogen carbonate. The other possibility is that you might have a patient who's expelling too much carbon dioxide. This is the panicked patient, the one that's hyperventilating. They're breathing in and out too fast. They're doing it probably because they're anxious or panicking. Because they're exhaling so frequently, they're exhaling too much carbon dioxide. So they're losing carbon dioxide out of the body. If you're losing that, the equilibrium is going to shift this way to replace the missing carbon dioxide. That means that we're losing this stuff because it got spent to come up to there. meaning that this equilibrium is shifting that way. And with that equilibrium shifting that way, the concentration of the hydrogen ion drops. The pH rises. It's called respiratory alkalosis because their blood is becoming too alkaline. So we have really two conditions of the bloodstream that are related to pH. Respiratory acidosis, when the blood becomes too acidic. Respiratory alkalosis, when the blood becomes too basic. Your blood is set to buffer for small issues with carbon dioxide, but these are medical issues that result in large swings in the amount of carbon dioxide. You've seen probably on old sitcoms, people who are hyperventilating, they give them a paper bag to breathe into. What the bag is doing is it's trapping the carbon dioxide right by the person's face so that when they inhale again, they inhale that carbon dioxide right back in again, effectively putting the carbon dioxide back into the bloodstream. So we can reverse this whole thing by making them breathe the carbon dioxide back in again. So breathe in this carbon dioxide, which pushes the equilibrium over here, which gets us extra of this, which pushes the equilibrium over here. The hydrogen ion concentration comes back up again. And the pH drops back to normal again. The limitation of this buffering system is that you can only have a certain concentration of things in your bloodstream, and that certain total concentration ends up being 0.03 molar. You can't have a total concentration of anything in your bloodstream that exceeds 0.3 molarity, and so you can only have a very limited amount of these things in your bloodstream. And so your blood can't be an extremely good buffer. It can only buffer against minor changes in carbon dioxide. And when your body starts to not function properly, you get major swings in CO2 concentration, and your blood is unable to compensate for that. Okay, so that kind of wraps up the stuff that goes with buffering. There was one more little piece to the target that went with went with acids and bases, and that was 4.1J. There are some practice problems that go with buffers in 4.1J, so that is part of your homework. We'll decide on what we're going to do with the rest later. And then we just need to take a look at a few other units of concentration. But why don't we take about a 5-minute break, reconvene at 9 o'clock. So if you need to use the restroom or just take a lap around the hall, get up, move around a little bit. We've been kind of heavy here on having to explain what we learned yesterday. So take a little break.